This is our last section in Chapter 5, Conditional Probability and Independence. So, two events, A and B, are independent if the occurrence of one event does not change the probability that the other event will happen. So here are some formulas to show it. So if A and B are independent, then A given B is probability of A, and then probability of B given A is probability of B. And then also probability A given B is equal to the probability of A given not B. They are the same. So if you take a condition off and they're equal, then they are independent. So this is different from mutually exclusive. So let's see. If the in the Diamondbacks example, are the events tacos and win independent and explained? So here is our two-way table that we created a couple of sections ago, or it might have been last section. And we want to see if they're independent. So we would check these things. So probability of taco is 30 out of the 81. And then probability of taco given win was 26 out of 41. And probability of taco given not win was 4 out of 10. So we look at each of these. So each of these, remember they said that the way you get a taco is if they have 6 or more wins. So this is probability of 6 or more wins. This is probably a 6 more runs, sorry. Probably a 6 or more runs given a win. And then this is probably a 6 or more runs given a loss. So none of these are equal. So these are not independent. So it's more likely to get free tacos, 6 plus runs, if they win. So these are not independent. So you'd show that those probabilities are not equal, and that shows that they're not independent. But if they were equal, it would show that they are independent. Okay, let's look at this next example dealing with the finger length. Is there a relationship between gender and relative finger length? To find out, we use a random sample at the U.S. Census at School website. Okay. To randomly select 452 U.S. high school students who completed a survey. The two-way table shows the gender of each student and which finger was longer on their left hand, index or ring finger. So here's a two-way table that was given to us. So they surveyed 452. This one says female with longer index finger was 78. Female with longer ring finger is 82. Female that had the same length with ring finger and index finger. And then we can go down the male side as well. Okay, so are the events female and has a longer ring finger independent? So here's female. And then longer ring finger is right here. Oh, female is here, 212, sorry. And then let's see. So probability of the ring finger being longer. So here we go. Ring finger, 234 out of the 452 total. So that is probably having a longer ring finger. Probability of ring finger given female. So that'd be the 82 out of the 212, which gives us that. They are not the same. So they are not independent. The two probabilities are not equal. So the events female and longer ring finger are not independent. Knowing that a student is female makes it less likely that her ring finger is longer than her index finger. Okay, general multiplication rule for independent events. And is it on the formula sheet and how is it related to the multiplication rule? Okay, so here is our rule for independent events. So the probability A and B can be found by probability A times probability B, but this is only true for independent events. This is not on the formula chart. But remember how we talked about the coin being tossed? Each of those are independent of each other, so you would just multiply half times half. Okay, so how is it related to the general multiplication rule? So remember this, probability A given B is probability A and B over probability of B. And probability A intersect B is probability B times probability A given B. So all of these formulas. So if we know that they're independent, we know that this is just going to be probability at A. So I would just change this to probability at A. I don't know if I have that. Yeah, I do. Probability at A given B is just probability at A. So that's why you have probability A times probability at B.
Okay, so that was the independent formula. It says, what's the difference between mutually exclusive and independent? So here's an example. Probability of a red card, probability of a club. So A is a red card, B is a club. Probability of getting an A is 0.5. But probability of A given B, so probably it's red given it's a club, never going to happen. So that's 0. So this is mutually exclusive. But see how they are not equal? So that tells us it's not independent. Here's another example. Probably a red card and B is 7. So it says probability of A, probability of a red card is half. Probability of a red card given it's a 7 is 2 out of 4, which is also a half. So you can have a red 7, so that's not mutually exclusive. But see how these probabilities are equal? So that tells us they are independent. Okay, example 3. A is a red card, B is a heart. Probability of getting a red card is half. Probability of red card given heart is 1 because all hearts are red. So that's an absolute guarantee. So these are not equal, so it's not independent. And red card, heart, not mutually exclusive because you can have red card and heart. Okay, so two mutually exclusive events can never be independent. So that is the important thing to get from here. Okay, first trimester screen. The first trimester screen is a non-invasive test during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to the study, published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a false positive result. Among 100 women with normal pregnancies, what's the probability that there is at least one false positive? So, something to take from this is 5% will be a false positive, right? 5% of normal pregnancies will receive a false positive. So that means the other 0.95 are going to get a negative. So we are going to use this as our starting place. So probability of at least one positive is 1 minus P of no false positives. So false positives was 0.5. So no false positives would be that 0.95. So P of all negative. So it's for all 100 women, we do 0.95 times itself 100 times. And then we get this. Okay, so it's possible because it's reasonable to assume different women's results are independent. My results compared to my next door neighbor's results are going to be independent of each other. So we're able to multiply the probabilities. So it's possible because it's reasonable to assume different women's results are independent of one another. So we are going to take this and plug it into this formula. 1 minus the no false positives, and we get 0.9941. So let's write what that means. Let's summarize. Over 99% probability that at least 1 in 100 women will get a false positive. 1 out of 100 women. So if 100 women go in there, it's guaranteed at least one of them will get a false positive. I guess not guaranteed, but that's a pretty high probability. Okay, the next one. Weather conditions. On a recent day, the Dallas Morning News forecast 50% chance of rain in Arlington and a 50% chance of rain in Mansfield. What is the probability of rain in both locations? So, is raining in one location close to another area? Are those independent of each other, or is there some kind of relationship there? They're dependent on each other. So we cannot answer this. We cannot multiply 0.5 times 0.5 because these are not independent. So we can't answer because these events are not independent. Since knowing it is raining in Arlington most likely indicates it is also raining in Mansfield. Sorry about that typo. So it's not independent events, so we cannot multiply. You would need to know probability of one location given the other in order to do anything with that. All right, that is it for these notes.